Assalamualaikum and good morning everyone. We are from Group 22 and today we will be presenting a very important concept in linear algebra, eigenvalues and eigenvectors. This topic may sound complex at first, but we will break it down step by step with definitions, examples and some simple calculations. Before we begin, let me quickly introduce our group members. I am Noh Farahanis and with me are Tan Junjing, Imran Aizul, Lim Weng Yan and Siti Mariam. Let's get started. First, let's understand the basic definition. An eigenvector is a special vector that when multiplied by a matrix A does not change direction. Instead, it gets scaled by a number called the eigenvalue, denoted by lambda. So, instead of rotating or bending, the vector simply stretches or shrinks. This relationship is written as Ax equals to lambda x, where A is a square matrix, x is the eigenvector, lambda is the eigenvalue. We will show how this works with an example in the next slide. Let's take an example to apply what we just learned. We are given a matrix A equals 3, 0, 8, negative 1 and x equals 1, 2. We want to check if x is an eigenvector of A and whether its corresponding eigenvalue is lambda equals to 3. To verify this, we multiply A by x. Ax equals to 308 negative 1 times 1, 2. Calculating this, we will get Ax equals to 36. Now, check for lambda x. As we know, lambda equals to 3. Thus, lambda x is equal 3 times 1, 2 and we will get 36. Since Ax equals to lambda x equals to 36, we confirm that x is an eigenvector of A and the corresponding eigenvalue is lambda equals to 3. This step is very important when verifying solutions in exams or applications. Now that we understand the concept, let's go through the steps to find eigenvalues and eigenvectors on our own. Firstly, we form the matrix A minus lambda I, where I is the identity matrix. Next, we calculate the determinant of this matrix and solve determinant A minus lambda I equals to 0. If needed, especially for higher order matrices, we can use long division or factoring to simplify the polynomial. And lastly, once we find the eigenvalues lambda, we plug each one back into the matrix equation. A minus lambda I multiplied with x equals to 0. And then from here, we solve for x. Before we move on, here is something important to take note of, especially when you are dealing with different matrix size. If the matrix is of size n times n, then you will always have n eigenvalues. For example, a 3 by 3 matrix will have 3 eigenvalues, and a 2 by 2 matrix will have 2. These eigenvalues might not always be distinct. You might get repeated values, which we call repeated eigenvalues, or even complex numbers if the solution involves imaginary roots. So, even though the steps are straightforward, the solutions you get can vary, and you will need to know how to handle all three types, which is real, repeated, and complex eigenvalues.
For example 1, we let A equal to 4, 2, 1, 3. First, we construct A minus lambda on diagonal matrix. Then, solve for determinant A minus lambda I equal to 0. Then, we got eigenvalues lambda 1 equal to 5, lambda 2 equal to 2. Next, we need to find its eigenvector for lambda equal to 5. From SLE for eigenvalues, we got eigenvector 2, 1 for lambda equal to 5. For example 1, we let A equal to 4, 2, 1, 3. First, we construct A minus lambda on diagonal matrix. Then, solve for determinant A minus lambda I equal to 0. Then, we got eigenvalues. Next, we need to find eigenvector for lambda equal to 2. From SLE for eigenvalue, we got eigenvector 1, negative 1 for lambda equal to 2. Move to example 2 for symmetric matrix. We let A equal to 4, 1, 1, 4. Step 1, we construct A minus lambda I. Then, step 2, we solve for determinant A minus lambda I equal to 0. Then, we got eigenvalues lambda 1 equal to 5, lambda 2 equal to 3. Next, we need to find eigenvectors for lambda equal to 5. From SLE, for eigenvalues, we got eigenvector 1, 1 for lambda equal to 5. We also need to find eigenvector for lambda equal to 3. From SLE for eigenvalue, we got eigenvector 1, negative 1 for lambda equal to 3.
Next, so we know for this diagonal matrix A, the eigenvalues are just the numbers on the diagonal. For the example 3, the eigenvalues are 3, 2, and negative 1. Simple because diagonal matrices only stretch vectors along the axis, no fancy rotation. Now, let's find the eigenvectors for the first lambda, which is 3. So we solve A minus 3 identity multiplied by x equal to 0. Subtract 3 from the diagonal and all other entries stay 0. For the first x, we let x1 equal to 1. And then we will got the second x is 0 and the third x is also 0. So the eigenvectors is 1, 0, 0. Next, let's find the eigenvectors for the second lambda, which is 2. We use the same logic as the previous one, so the second x is free variable. So the eigenvectors will be 0, 1, 0. Lastly, let's find the eigenvectors for the eigenvalue negative 1. Since the third x is free variable because it's on the z-axis, so the eigenvectors will be 0, 0, 1. Diagonal matrices have eigenvectors lined up depends on the axis. Next, let's move on to the application of eigenvalue and eigenvector. The first one is Principal Component Analysis, PCA. Why does this matter? Imagine if you have 3D data like weight, age. PCA use eigenvectors to find the most important direction. PCA also use eigenvectors to compress data by keeping only the large eigenvalues. We also provide a YouTube link for more detailed explanation regarding this topic. Next, the second application of eigenvalue and eigenvector that we are going to present is applicable in quantum physics. So in quantum mechanics, eigenvalue is used for energy levels, for example, electron orbits. Next, eigenvector is used where the particle live, to show how the particle live. Fun fact, this is how we actually predict the atomic behavior. We also provide a must-watch video about quantum mechanics. Last but not least, remember that if we get diagonal matrix, the eigenvalues will be on the diagonal and the eigenvectors will be on the axis. That's all from us, Group 22. Thank you.